Hi again, everybody. Chris Tisdale here. Thank you for tuning in. In this video, I'm going to continue my series on geometry and geometric construction using a circle arc template and a straight edge. And in particular, in this video, we're going to do a forbidden construction. We're going to trisect a given angle. And we're going to use a slight extension of the straight edge called a Neusis straightedge. And the problem of angle trisection has mystified mathematicians for thousands of years. Given an angle, can you form a new angle that's 1/3 of the original angle size? So it turns out that all the efforts with a compass and an unmarked straight edge were in vain, because it was shown that these two tools alone, it's impossible to trisect an angle. So we're going to use this circle arc template and a Neusis straightedge. So how do you do it? Well, I'm glad you asked. Let me share my screen with you and we can have a look. So this is the tool we're going to use. You can see there is an extended circle arc template here. And then on the side, down here, it says Neusis straightedge. So a Neusis straightedge is basically a straight edge which has no markings on it, apart from 2 points. And in this setup, the distance between this point P and this point R is exactly the radius of your circle arc template. So can you trisect an angle with this? Yes, you can. So let me show you how it's done. I'm going to start over here. And I'll sort of just draw in the initial data. Okay, so let's say we've got A, B, and I'll draw in an angle. So let's say we'll start there. Okay, and let's call that point C. All right, so the question is, can you trisect angle, we'll call this, say, 0. Can you trisect angle B0C? Okay, just using your circle arc template and this Neusis straightedge. And the answer is yes, and the number of moves are not very complicated at all. So I'll show you the moves first, and then I'll do a little bit of justification. So let's place the center of our circle arc template at the vertex O, and we're going to draw around this arc so it cuts the line segment AB and OC. Okay, so that's the first step. Now we don't need the circle arc template anymore. So let's move on to the straight edge. So you see we've constructed 2 points here and here, and we won't need them, but this point here is very important. Let's call that point D. And we're going to construct a line in the following way. I'm going to put my pen at D, and I'm going to wiggle my Neusis straightedge around until both points align with the line segment AB and the arc that I drew earlier. Okay, so now obviously you can't do this with an unmarked straightedge. And then I'm going to rule a line until I cut AB and the arc. So I've got a new point there. Let's call it E, which is the intersection between this line segment and the arc. Okay, so now I'm claiming that the angle EAO is 1/3 of the angle COB or DOB. They're the same angle. Okay, let's actually test that, have a little measure, and see what we get. So if I measure in here, the angle here looks like it's about 35, okay? So the angle over here should be around about 12. Let's just have a look. Yep, that's pretty close. Okay, so we're pretty close there with our construction, but why does it work? That's a really good question. So let's see if we can justify that this angle really is 1/3 of this angle. So to do that, I'm going to just draw in this line segment from O to E. Okay, now we're going to use properties of triangles, the sum of the angles of triangles. We're also going to use the sum of the angles of a straight line. Okay, now because the way we've designed this Neusis straightedge, where the distance apart is exactly the same as the radius, it means that that's a radius, that's a radius, and that's a radius. So all of these line segments have the same length, and that, so you can sort of see, oh, there's an isosceles triangle here, there's an isosceles triangle there. We're going to use those characteristics. Now notice I haven't labeled this point. I am going to label it now. Let's put that as F. Okay, so FEO is an isosceles triangle, EOD is an isosceles triangle, and what that means is that angle and that angle will be equal, that angle and that angle will also be equal. Okay, so let me grab my notes here and we can talk a little bit about the proof. So let's call that alpha. Trisect alpha. Okay, so the standard proof for this starts with 180 degrees being in this straight line here, and then what you do is you express this angle EOD in terms of EFO or EOF. Okay, and then you do a little bit of algebra. Okay, so let's explore that. So angle alpha plus DO angle DOE plus angle EOF equals two right angles, right? 180 degrees. Okay, and what we're going to try to do is get DOF in terms of angle FOE. So that angle and that angle are equal. That angle and that angle are equal because of isosceles triangles. Okay, so that's really what we want to work on here. Okay, so how do we do it? Well, we know that this triangle FEO is isosceles. So by the sum of angles, angle O, well, this angle plus this angle plus that angle equals 180. So they're the same. So let's write that in terms of FOE. Two times the angle FOE plus the angle FEO equals two right angles, 180 degrees. Okay, and this angle here also adds up to 180 degrees. So FE angle FEO plus DE angle DEO equals 180 degrees. Okay, great. All right, you can see here that we've got, hang on, hang on, let me adjust that. So triangle FEO is isosceles, so 2 FOE plus, oh, FEO, yes, that's right. Okay, so I thought I made a mistake. So if we look now, this and this are in both of these equations, right? So if we substitute them out, it means that this has to equal this. Okay. So you've got 180 there, 180 there, that angle and that angle. These two things both add up to 180. So that has to equal that. Okay. Great. Okay. So you can see now that we've actually expressed this angle. Oh no, we haven't done that yet. We've still got a little bit more to go. So, oh yes, so we've got the triangle here. So this angle here is going to be 180 degrees minus 2 times these angles, right? So 2 times angle OED. Okay, so that's just from the sum of areas, the angles of a triangle. Okay, so now angle DEO and OED are the same, right? So okay, so now I can get that into here and go, okay, well, it's 180 degrees minus 4 times angle FOE. So now we're at the stage where this angle is expressed in this angle FOE. Okay, so let's go back to this original one now. And we're almost done. Okay, so it's going to be alpha plus angle DOE, which is this, written in terms of FOE, plus EOF, which is the same angle, right? So FOE is the same as EOF. Okay, the 180s will cancel off. And then we're going to get alpha equals 3 angles FOE. And that's it. Okay, so this angle is 1/3 of that angle, and that angle is the same as that angle. So this angle must be 1/3 of that. Whew, okay, so a little bit longer proof. So quite a short construction, but a little bit longer proof. So what do you think? Let me know. I think it's really cool because, you can basically do, just by adding 2 markings, you can suddenly do a forbidden construction and do things that you can't do just with a regular compass and an unmarked straight edge. So let me know what you think. Now, there are also other tools. You don't have to use this like an unmarked straight edge to trisect these angles. So there's all sorts of other things you can do. But anyway, I hope you found the forbidden construction interesting. I'm going to continue these videos. Hope you're finding them useful or valuable or interesting. And take care. All the best.